Welcome to the second session for today. I'm Vadim Makarov. I will chair the session, and my colleague Shan Zhan will handle the questions and answers. If you have questions to the speakers, please type them in the Q&A box in Zoom. I pass the podium to Ernst Tan for the first presentation.
Okay, thank you. Okay, so good morning or afternoon, everyone. So today I'm presenting a result on improving the robustness for device-independent QKD. This is a joint work with some collaborators from the Center for Quantum Technologies in Singapore, as well as the Leibniz University, Hanover. So device-independent QKD is based on the observation that if you have a violation of a Bell inequality, then in fact you can prove the security of, say, QKD without having to trust that the measurements are being performed in the expected manner. So it's possible to construct a security proof where you don't trust what measurements the devices are performing. So this helps to reduce the number of assumptions in the security proof, which may also help to reduce the attack surface on the protocol. However, the drawback of this stronger sounding form of security is that there is less noise robustness for the known security proofs. So currently the known DIQKD protocols, they are not very robust against noise. And because of this, we don't really have a full experimental demonstration of DIQKD at this point. The main point of this work is a modification to DIQKD protocols such that we can improve their noise robustness. And the key observation that we use in this work is essentially this trick here, which is that for many of the standard DIQKD protocols, you mainly use one of the measurements for key generation. So for instance, Alice's measurement A0 is the one that's mainly used for key generation. But if we think back to the earlier QKD protocol proposals, quite a number of them were based on sifting, in the sense that you pick your basis choices uniformly at random, and then you apply a sifting step at the end of the protocol. The reason why we might expect, in fact, some cases where the key rate from the sifting-based protocol is higher would be that if we consider the case where you only use one measurement for key generation, A0 here, you have to allow for the possibility of it being the worst case measurement, in the sense that it's the one that leaks the most information to Eve. On the other hand, if you use your uniformly random basis choices, then you can show that if there is any non-trivial CHSH violation, the two measurements have to be different measurements. And in particular, this means that you cannot have both of the measurements being the worst case measurement. And this is why you might be able to expect some amount of improvement from using the sifting-based protocol instead. But computing the key rate from this sifting-based protocol is a little bit challenging. We developed some approaches in this work to help tackle this task. But for the purpose of this point, I'll just quickly summarize the results that we got from our approach. So on this graph here, it's a region plot where the axes are the QBER and CHSH values from several Bell test experiments. And the coloring of this plot is that the blue regions here are where we can show that there's a positive key rate from the sifting-based protocol, where darker shades of blue refer to higher positive key rates. And the important point that we want to do is to compare this against the results for the standard protocol, which is shown in this graph here that was taken from a previous work. Although the color scheme for this graph is that the green region is where positive key rates are achieved. And for now, I will draw your attention to specifically to the Bell test experiments that are highlighted in this blue box here, because these are the loophole-free Bell test experiments. And each of these experiments is plotted as a corresponding point on this graph together with its error bars. So for the standard protocol, we can see that one of the Bell tests, loophole-free Bell test experiments is just on the border of achieving positive asymptotic key rate using the standard protocol. This is experiment number 7, which is the NV Center Bell test. On the other hand, if we instead use a sifting-based protocol, our results show that this is able to achieve a clearly positive asymptotic key rate, because this is clearly within the blue region. And in addition, there is another Bell test that enters the region of positive key rates, which is the one based on coal atoms. So we can see that using a sifting-based protocol, you can have at least 2 kinds of Bell test implementations that, at least in principle, achieve a positive key rate asymptotically. On the other hand, for photonic experiments, it seems like our approach doesn't manage to guarantee a positive asymptotic key rate for them. But I'll just briefly mention that for photonic experiments, there's a different approach that may be more promising. It's known as noisy preprocessing, which is a technique from standard QKD. We released a result on this a few months ago, and we are presenting it during the poster session later today, if you would like to take a look for the photonic setups. But with these results in mind, the key questions that remain to be addressed, one of the important things that we should tackle would be the finite size analysis, because one important difference between the various Bell test implementations is that they have extremely different sample sizes. So even though we can now claim that some of the Bell test experiments are in principle able to achieve a positive asymptotic key rate, the sample sizes in the actual experiment may not be large enough to certify a key rate with when you consider the finite size effects. So we are in the middle of preparing the finite size analysis of these protocols, so that we can compare the different Bell test implementations. As a small helpful side effect, we are also proposing a modification to the analysis that allows us to potentially remove the sifting factor, because if you have to sift out about half the rounds for mismatch basis choices, this is quite a heavy penalty to the key rate. And in addition, we are also looking into whether this approach of using uniformly random basis choices can be combined together with noisy preprocessing. So we are also currently developing this approach, and there are several other advantages available using this optimization method that we are now developing. If you would like to hear more details about it, it's described in the full talk, and I can also discuss it during the question session. And with these results in mind, well, it would be nice to try and attempt an experimental implementation of the IQKD at this point. So we would have to look very carefully into the experimental parameters and try to optimize them for a demonstration. This is fairly challenging because there's many parameters to optimize, but we have a few ideas in mind that we are investigating. And yeah, I guess to sum up, so we have made the observation that if you use a sifting-based protocol for the IQKD, you can substantially improve its noise robustness, and some Bell test experiments may potentially be able to achieve a positive asymptotic key rate at this point. Yeah, I guess that wraps up my presentation. I'll be glad to have your questions afterwards.
Thank you, Ernest. The next speaker is Wen Zhao Liu, please.
Sorry, let me just, okay.
Can you see the slides?
Yes, please go on.
Okay. Hello, everyone. Thanks to the organizer to give me this opportunity to present our recent work, Device-Independent Randomness Expansion Against Quantum Adversary. My name is Wen Zhao Liu. I come from the USTC, the University of Science and Technology of China. This is a joint work with Professor Roger Kovac, who provides theoretical support. I and my colleagues in the USTC are mainly responsible for the experimental part. You can find more details on our archive paper. First, let me briefly introduce the random number. It can be defined from two aspects. One is that the random number needs to obey uniform distribution. The other is that it should be unpredictable, which means that it should be independent of anything else. Since random number has many applications in our lives, we have motivations to do some research. The first is to build a well-random number generator. For a classical one, its output could be well uniform, but it is predictable in principle. In the case of quantum, it is unpredictable in principle, because this is guaranteed by the intrinsic randomness of quantum mechanics. Let's come to the schemes to realize randomness generation. We just consider a simple physical model using a 50-50 beam splitter to generate a raw string. And then we estimate the amount of randomness, which should be unpredictable to adversary. Finally, we extract the uniform random bits by classical processing. However, for real devices, it is difficult to find a complete physical model that could describe all of the physical processes in a random number generator. Besides, how much randomness could be extracted from the raw string is also not an easy thing to calculate. Another motivation is to check a candidate random number generator working correctly. Up to now, we could not find any good test that only acts on the output. Based on these ideas, we find that the device-independent protocol is a good way to realize a real random number generator. The figure is a conceptual diagram of the device-independent protocol. We do not care about how it works in the black box, but only consider the joint probability of the input and output, as long as it proved to violate the Bell equality. The output must contain unpredictable randomness. This protocol can be used to check a candidate random number generator and also easy to check. Not focusing on the specific devices makes it general and could against different attacks, but difficult to experimentally achieve. Here I list the experimental demonstration of DI-QRNG. It can be found that in all demonstrations, the amount of output is much smaller than the input. Considering the need for the large amount of randomness in practical applications, DI-QRNG is not enough. Therefore, we hope to realize device-independent randomness expansion, where the generated randomness surpasses the consumed. For the DI randomness generation, in each round, the randomness consumption is always 2 bits, and the randomness generated could never more than 2 due to the correlations between A and B. In order to achieve expansion, we need to reduce the entropy consumption. As shown in the figure, we adopt the spot checking protocol to realize the net gain. We say Ti satisfy a distribution gamma and 1 minus gamma. If Ti equals 0, the input of Alice and Bob, Xi and Yi are both 0. If Ti equals 1, each unbiased random number generator will be triggered and produce random number uniformly. We could obtain the CHSH value according to the joint distribution in the test rounds. During the implementation of protocol, there is a condition related to the accumulated CHSH value to decide whether to abort. If the protocol succeeds without stop, we estimate the amount of randomness and perform extraction. This is our experimental setup. The system is located in a single lab. A is the entanglement source. The entangled photons are generated by spontaneous parametric down conversion and are delivered to measurement sites. B represents the measurement sites, Alice and Bob. Each of them uses a pixel to project the single photon into one of 2 predetermined measurement bases, and then detects single photons with a superconducting nanowire single photon detector. In our experiment, we do not close the locality loophole. In order to satisfy the non-signaling condition, we use shielding assumptions to prevent the potential communications between Alice and Bob and also between biased QRNG and measurement sites. We also realized randomness expansion in a separate work in which the locality loophole was closed in the test rounds. The setup used the same platform but differs in the location of Alice and Bob, who are instead at 2 remote sites. As a comparison, we analyze its performance using the same theory with the same error parameters as before. In our experiment, we use the entropy accumulation theory, EAT. By using the smooth mean entropy to estimate the amount of randomness, the EAT method provides relatively tight bounds on the amount of randomness that can be extracted against quantum adversary. For the randomness input, since we use a strong extractor, we did not take the state for extraction into account. Now let's come to the results. There are 2 figures on this slide. The figure A is the minimum number of rounds to witness randomness expansion. To better show the progress in our experiment, we made it a comparison with our previous DI-QRNG work, which is the open square in figure A. It would take at least 118,000 hours to witness expansion with our revised EAT method, which is too long in practice. The circle and cross represent the minimum number of rounds to witness expansion with our platforms. In our experiment, we achieved the expansion protocol in 220 hours for the experiment with space-like separation and 19.2 hours for our main experiment. The figure B is the randomness expansion rate versus number of rounds. Our results are represented by the cross and circle. The asymptotic rates are only decided by the CHSH value. We notice there are 2 related works. One is another work of our group with the quantum probability estimation framework, QPE. This theory was initially developed by the NIST group. They also achieved the random expansion. Please see the next talk by Yanbao to find more details. Let me make a brief summary. We achieved the randomness expansion with the revised EAT theory and complete the experiments independently with 2 different experimental platforms. For the future, on the experiment, we plan to continue to improve the performance of our system, and we can also do some practical shielding methods to make the experiment more convincing. On the theory, maybe the EAT method could be further improved to get more randomness, and also a detailed comparison between the EAT and the QPE is also meaningful. That's all. Thank you for your attention.
Thank you, Wen Zhao. The next speaker is Yanbao Zhao, please. Unmute yourself, please. You are muted.
Oh, sorry. So
now it's fine.
Can you hear me? Oh, okay. Sorry. So thanks for the introduction. Hello, everyone. I'm going to present our recent work on device-independent randomness expansion. So this work is a collaboration among several institutions. The experiments were performed at NIST, led by Crystal. High-efficient single-photon detectors were developed by Siwoo's group. The quantum random number generators used are from Morgan's group. I worked with Mohammed Honghao Mani on the theory side of this work. So first, let me briefly introduce device-independent randomness. As you already heard from Wen Zhao, so in the device-independent case, we do not need to trust a quantum device. So we model each device by a black box. The main idea is we can perform a Bell test. We can test a Bell inequality to see whether there is a violation of local realism. If there exists a violation, so the outputs of the tests are not deterministic functions of the inputs and any other set information, such as local variables. So in this case, so the outputs must contain intrinsic randomness. Since we do not trust a quantum device, so we call this device-independent randomness generation. Next, let me briefly explain what is randomness expansion. So by performing a Bell test, we get a sequence of outputs. We can certify the amount of randomness in the outputs. After that, we can run an extractor to get a short sequence of uniform bits. Over this process, we use random bits for performing the Bell tests. Also, we use the random bits for running the extractor. Randomness expansion is achieved if the amount of output randomness is more than the input randomness. As already heard from Wen Zhao, until recently, device-independent randomness expansion has not yet been demonstrated. People proposed to use the spot checking protocol to achieve randomness expansion. But for running this protocol, we use both uniform and non-uniform random bits. We use non-uniform random bits with a specific bias to decide whether a trial is a spot checking trial. In a spot checking trial, Alice and Bob just perform a Bell test. We use uniform bits to determine the inputs of Alice and Bob for the Bell test. However, in practice, it is not easy to access non-uniform bits with a specific bias. To avoid using non-uniform bits, we develop a protocol called the Blockwise spot checking protocol. In this protocol, we group experimental trials into a sequence of blocks. Each block has a random number of trails. Specifically, we use key bits to choose the number of trails in a block. The last trail in a block is a spot checking trail, where Alice and Bob perform the bell test. For the other trails in a block, Alice and Bob just use fixed inputs. Similar to the usual spot checking protocol, we can make something like the untrusted devices can't learn in advance when a block will end with a spot checking trail. In this case, we can certify randomness generated from every trail in a block. At the same time, you can see each block consumes only key bits for determining the number of trails in the block. Also 2 bits for the spot checking trail, the bell test in the spot checking trail. So it's possible to achieve randomness expansion. Next, let me briefly describe our experimental implementation. We use a loophole-free bell test configuration. Alice and Bob are far away from each other so that we can ensure their measurement processes are space-like separated. Also, Alice and Bob perform measurements with high-efficient single-photon detectors, so we can close the detection loophole. In the protocol, we also use a trusted third-party spot to determine the number of trails in a block. Specifically, Spot uses 17 random bits from a NIST randomness beacon for this purpose. We use 17 random bits according to our security analysis. Over 2 weeks, we collected enough data for expansion analysis. Our main result can be summarized into this plot. Here you can see the amount of output random bits change with the number of blocks analyzed. So at the beginning, we can't certify output randomness. After some point, the output randomness surpasses the input randomness. And after 91 hours in experiments, our success threshold was satisfied. So we successfully achieved randomness expansion. These experiments took about 2 weeks. However, it can generate much more randomness than the NIST randomness beacon in the last 3 years. With this, I would like to stop. Thank you for your attention.
Thank you very much, Yanbao. The next speaker is Victor Zapatero.
Can you hear me?
Yes, go on, please.
So, good morning. My name is Victor Zapatero. Thanks a lot to the organizers for making this online QCrypt possible. And for those of you who didn't watch the long video presentation, this work is a collaboration between the University of Science and Technology of China and the University of Vigo in Spain. And what we do is we report on the first QKD experiment secure against malicious QKD equipment based on the use of redundant devices and distributed post-processing. The motivation behind this work is the unjustified assumption that the devices used by Alice and Bob in a QKD session are honest. And I say unjustified because our experience in classical crypto indicates so. Malware, backdoors, covert channels, and things like this are also expected to affect quantum crypto because the manufacturer of the equipment may provide it with plenty of opportunities to sabotage the devices before they reach the end users. So in the first place, I would like to comment on some unsatisfactory attempts to eliminate this honesty hypothesis. And the first one is probably DIQKD. When talking about malicious devices, this idea may come to our minds. However, the so-called memory attacks illustrate that DIQKD is not secure if the devices are not only faulty or uncharacterized, but actually malicious. And the fundamental weakness that remains even in the DI setting is the simple fact that the final keys are classical objects that can be copied. On the other hand, the ideal solution consists of Alice and Bob validating the integrity of their system, of every component. However, this kind of post-fabrication tests are typically very time-consuming, and actually they can be evaded in practice. So, what is the main idea behind our QKD experiment? The idea is the following argument raised by Marcos Curti and Hoi-Kwon Lo. Probably it is harder for you to corrupt various devices than a single device, especially if they originate from different vendors. Therefore, the parties should use a redundant number of devices and assume that a limited number of them is corrupted. And if this is the case, security can be restored by combining verifiable secret sharing and privacy amplification, which are two well-known techniques. And crucially, this is the best one can expect, because QKD will be insecure if multiple devices are compromised, not just one QKD system. And it is up to the users to decide how many corrupted devices they want to be protected against. But before I move with the talk, I would like to distinguish the two different parts of a QKD setup, which are the QKD pairs or the QKD modules, which are these two blue boxes linked by a quantum channel and are responsible for the quantum communication phase, and the CP units, which are the pink boxes linked by authenticated classical channels that implement the post-processing of the raw data into the final keys. In standard QKD, where the devices are trusted, it suffices for each party to have one device of each kind. However, if malicious devices are considered, a different setup is necessary. And the one we suggest looks like this. Essentially, it is based on redundancy. What we need is multiple pairs of QKD modules or QKD pairs and multiple CP units per lab, together with some extra classical authenticated channels. And if this is the case, security can be restored as shown by Marcos Curti and Hoi-Kwon Lo with the following assumptions. At least one QKD pair is not corrupted. Less than one-third of the CP units are corrupted in each lab, and Eve is assumed to fully control all the corrupted devices. And as I said before, the tools to establish security are verifiable secret sharing and privacy amplification. And now we can see how these two tools combine. And this takes us to the rationale behind our protocol. In the first place, multiple QKD sessions take place. Okay, so in each session, a QKD pair obtains its own raw key. And then the post-processing of these raw keys starts. And here is where verifiable secret sharing comes into play. The post-processing of each key is performed redundantly to assure correctness, and the key material is divided into random shares to assure that they are kept private through the process. And crucially, the linearity of the post-processing operations makes them very easy to implement in the multi-party setting. And at the end of this distributed post-processing, privacy amplification is applied, also redundantly and share-wise, to remove not only the information that it learns from the quantum channels, but also the key material that comes from the potentially corrupted QKD pairs. So now our experiment is just a particular example of the protocol I just described, where we implement a 1.25 gigahertz polarization encoding MDI QKD system with a silicon photonic modulation chip. And we only provide Alice with redundant devices. Specifically, we protect her against one corrupted device of each kind, exactly. So one CP unit and one QKD module. And in this slide, you can see a schematic of the setup, the secret key length we extract, and some experimental parameters. And more details can be found in the long video presentation on YouTube. And that's it. Thanks a lot for your attention.
Thank you very much, Victor. I pass to Sean for the Q&A session.
Okay, and then we thank all the speakers, but unfortunately, there is no any question. Okay, there is one question from larvae.
Okay,
there is a question, buddy. Yeah, and then I will let you to ask question. This is a question.
Okay, thank you.
Yeah.
Question for Victor.
Oh yeah, it's a beside to use. Okay. It's a question from larvae, Emilian, Claude to Victor. It's a bit sad to use many devices and to kind of waste their performance just to ensure that at least one pair is working properly. Would it be possible to have an assumption on the maximum number of corrupted modules to extract more key rate from the combined use of non-corrupted devices? For example, if 3 QKD devices are used but only one is corrupted, it would be nice to effectively use the key of the second non-corrupted devices. Victor, please. You can also see the question in the Q&A.
Okay, I'm not sure if I understand. Is he asking if the keys obtained by the corrupted devices can be also used for the final key, like not removing them with private simplification? If it takes too long, maybe we can talk in the meet and greet room, because I don't think I understood properly the question.
Yeah, I think he just suppose you have some junction that suppose only one is corrupted. It'll be effectively for your protocol. Can I read the question in the Q&A?
Yeah, if that is the way I can read it, okay.
Yeah, you can read it.
So, so the assumption is that you need one honest QKD module at least, okay? That is what you need. And if you have that, then you of course can extract a key, but that is the worst case scenario. If it is up to the users to decide their assumptions. So maybe they can decide that more than one pair of QKD modules are honest, and in that case, they will be capable of extracting a longer key, but that is up to the users. There's like some sort of security policy, and they make the choice of, okay, at most we have 2 or 3 corrupted pairs. But of course, to save resources, what you will do is something like, and this is how we thought about this, you will do something like, okay, if I want to have one secure pair, one trusted pair, at most I'm going to need, let's say, 5. Like, I am sure that 1 out of 5 will be safe. Or maybe someone else is like, if I have 2, probably one of them is safe. It's up to them, okay? Like the minimum amount of devices to obtain 1 key. That's how we thought about this.
Okay, thank you, Victor. And then Vadim, please ask your question.
Oh, I also had a question to Victor. So if we wanted to implement this protocol on standard QKD hardware, would you only need to modify the software? Would you need to make changes to the hardware? So imagine we have a commercial network installed and the user has like 2 QKD devices, 2 different vendors. Can the existing today's QKD network actually run this protocol with minor modifications?
Yeah, essentially you only need software modifications, okay? Because actually this experiment, in the longer talk, there are more details about the experiment. The experiment was done by Feihu Tu and Wei Li, and they use kind of the same setup, like something they already had from previous experiments, as far as I know. So you don't need new hardware, okay? This QKD pairs, like they implement independent QKD protocols, QKD sessions, like independent ones. And then the post-processing, what you need is essentially, because the more resources are basically involved in the post-processing, but the post-processing can be done by computers, like laptops. In our experiment, they were standard computers. So you don't need new like quantum hardware to implement this redundant devices idea. You don't need that.
Okay, and then I noticed there is one comment from Erica Anderson. I think it's just comment to the previous question. If I understood correctly, at most 1/3 of the devices can be corrupted. That's the assumption. That's yeah.
Okay. There exists 2 different kind of devices. So we make a difference between the devices that implement the quantum communication, which are the ones we call QKD pairs, and then the ones that implement the post-processing. Okay, so we distinguish, like the users can decide how many QKD modules, the ones that implement the quantum communication, are corrupted, and how many CPU units, like the computers that implement the post-processing, are corrupted, okay? The first kind, the ones that implement the quantum communication, you need one of them to be honest to be capable of obtaining a key, a positive key. But the second kind, which are the CPU units, since you need redundancy and you need things to be post-processed by a majority of honest units, you need that at most, actually less than 1/3 of them, of your computers, are corrupted, okay? So the simplest case is you have 4 computers, you can tolerate 1 corrupted one in the post-processing, for instance.
Okay, another question for you. It's also from Eric Anderson. It's in commercial QKD setups. The post-processing is likely hardwired and cannot be modified.
I don't know how to answer that. So in commercial QKD setups, hardwired, what does that mean?
I think it's probably using the FPGA program that you just you first have the logic and then you input in the FPGA, something like that. Yeah.
Yeah. So in our proposal, you need some extra classical channels that communicate some of your computers to the others and so on. Of course, it's more hardwired than standard QKD. That is something that you can't avoid. Of course, because we assume that Eve is very powerful and she fully controls all the corrupted devices. If you, for instance, assume that they don't collaborate with each other, like this computer is compromised by this vendor and this one is compromised by this other adversary, then you can reduce the number of computers, and so the setup is less hardwired, probably, I would expect.
Okay. I have a question for the Ernest. What kind of, for your theory, I think it's a good one, but what kind of attacking strategy are you using? I mean, is it a general coherent attack or just collective attack?
Right. Okay. So what we have currently written up is in the collective attacks analysis, although in principle, there is no obstruction to extending it to coherent attacks using the entropy accumulation theorem. But we are just doing that together with the finite size analysis. So yeah, it's not written in the work itself that it works against coherent attacks, but it's not too difficult to extend it to coherent attacks. Yes.
What do you expect the efficiency will change if you're using the
you mean whether the security analysis will be worse for the coherent attack case, you mean?
No, I mean the efficiency, because I think you probably need higher efficiency a higher hero-reading efficiency to get to secure against the coherent attack.
Well, in the asymptotic sense, it doesn't change things because for that it's possible to do a proof using entropy accumulation where the asymptotic rate for coherent attacks is the same as collective attacks. But for the finite size analysis, yes, there is some difference. There is some care that needs to be taken here, but in one sense, there's only a small difference between the collective and coherent attack situation, but it's possible to modify the protocol for collective attack situation in such a way that the finite size effect is smaller. But that really requires one to trust the collective attacks assumption. So mainly the difference is in finite size analysis, I would say, as an overall summary.
Okay, thank you. Any further question from the audience?
If there are no more questions, I propose that we move to this, how called, break room and see you there. You can ask, meet and greet room. So please move there and you can ask your questions directly to the speakers. And in the session room, we meet in 20 minutes for a tutorial by Eleni Diamanti. So thank you all the speakers and see you in 20 minutes.